Hi everyone, and welcome back to the channel. In today's video, we'll be tackling the detailed solutions for problems 2.1 to 2.4 from Chapter 2 of Griffiths Introduction to Quantum Mechanics. Let's jump right in and get started. Problem 2.1 is divided into 3 parts, and we'll go through them one by one, starting with the first. This part asks us to prove that for normalizable solutions, the separation constant E must be real. The problem also provides a useful hint to help us with the proof. The hint suggests we write the energy eigenvalue E as E sub 0 plus I times gamma, where E sub 0 is the real part and gamma is the imaginary part. We then need to demonstrate that for equation 1.20 to be valid for all t, the imaginary part gamma must be 0. This will ensure that the wave function remains normalizable. Before we dive into the solution, let's first do a quick recap of the Schrödinger equation and the method of separation of variables, which will be essential for solving these problems. The Schrödinger equation is the governing equation for the wave function in quantum mechanics. As you can see, it involves both time and space variables, which are mixed together in the equation. Since the Schrödinger equation is linear and homogeneous, we can apply the method of separation of variables to simplify it. The key idea is to assume a product solution for the wave function, like this. The wave function psi of x and t equals psi of x times phi of t. Here, psi of x represents the spatial part of the wave function, and phi of t represents the time-dependent part. Now we substitute this into the Schrödinger equation. Next, we evaluate the derivatives. First, the time derivative of the left side of the equation will give us psi of x times phi prime of t, while the spatial derivative will give us the second derivative of psi of x times phi of t. Now, we divide both sides of the Schrödinger equation by psi of x times phi of t. For the special case where the potential energy V does not depend on time, the right side is purely a function of space, and the left side of the equation is purely a function of time. This means that both sides must be equal to a constant, which we'll call E. So by applying the method of separation of variables, the Schrödinger equation breaks down into 2 ordinary differential equations, one for the spatial part and one for the time-dependent part. To solve the time-dependent part, we can use a bit of calculus. The left side of the equation can be written as the derivative of a logarithm by the chain rule. Now we integrate both sides with respect to time. Next, we exponentiate both sides to solve for phi of t. Now that we've solved for phi of t, we can plug it back into the equation we previously discussed, the product solution for the wave function, which was psi of x and t equals psi of x times phi of t. So after all these steps, the product solution for the wave function looks like this. Here a is just a constant that comes from the fact that the Schrödinger equation is homogeneous. And now we have the time evolution for the wave function, which allows us to proceed with solving the problem. Now let's get back to the solution of problem 2.1. From our recap earlier, we know that the wave function can be written as follows. We also know that the wave function must be normalizable, meaning the integral of the absolute value of the wave function squared over the entire domain must equal 1. This condition is provided as a hint in the problem. Note that we can express the absolute value of the wave function squared inside the integral as the product of psi and its complex conjugate. Now let's suppose that the energy E has an imaginary component. We'll write E as E0 plus I gamma, where E0 is the real part and gamma is the imaginary part. Now we substitute this expression for E into our wave function. Let's now plug this wave function into the normalization integral. Now, let's take the complex conjugate of the second part of the wave function. Note that the complex conjugate of the exponential part flips the sign of the imaginary component. After doing some calculus, notice that the factor involving E0 will cancel out, leaving us with just the term involving gamma. We can then pull this term outside of the integral. Now we can carry out the integration, and since the result must be constant because the wave function must be normalizable, for this to be true, the imaginary part gamma must be 0. Therefore, E is real. Let's now check Part B of Problem 2.1 from Introduction to Quantum Mechanics. In this part, we'll explore why the time-independent wave function can always be taken as real. Let's break it down. We know that the Schrödinger equation describes the state of a quantum system, where h is the Hamiltonian, psi is the wave function, and E is the energy of the particle. This equation gives us the allowed wave functions for a particle at a specific energy. Typically, the solutions to this equation can be complex. That means the wave function psi of x could have both real and imaginary components. But here's the important point. Griffiths tells us that we don't always need to work with complex wave functions. If psi of x is a solution to the Schrödinger equation for a given energy E, then its complex conjugate psi star of x is also a solution for the same energy. So if you have a complex solution, you automatically get another solution that's just the conjugate. Here's the key. You can combine these solutions to create real wave functions. For example, by adding psi of x and psi star of x, you get 1/2 times the sum of psi of x and psi star of x. This combination will always be real because the imaginary parts cancel out. This is really useful because the probability density psi of x squared needs to be real and positive. And by using real wave functions, we ensure that it behaves the way we expect. Plus, real wave functions are easier to interpret physically. Let's dive into Part C of Problem 2.1, where we explore the symmetry of wave functions. Specifically, we'll see how, if the potential is symmetric, the wave function can always be made either even or odd. Let's break this down step by step. Suppose we have a solution, psi of x, to the Schrödinger equation. Now let's make a substitution. We'll substitute x with negative u, where u is just a new variable. Next, let's look at the derivatives. We can use the chain rule to write the derivative in terms of this new variable. Now we can rewrite the Schrödinger equation in terms of the variable u. But here's the key point. Since u is just a dummy variable, we can replace it back with x. If the potential v of x is even, that means v of negative x equals v of x. This symmetry is crucial because it means both psi of x and psi of negative x will satisfy the same Schrödinger equation. Now, here's the exciting part. By the superposition principle, the general solution psi of x can be written as a linear combination of psi of x and psi of negative x. But there's more. We can choose the coefficients c1 and c2 to make the solution either even or odd. For example, it can be made even by selecting both c1 and c2 to be 1, and it can be made odd by choosing c1 to be 1 and c2 to be negative 1. Understanding quantum mechanics often requires drawing insights from classical physics. In Problem 2.2 of Griffiths Introduction to Quantum Mechanics, we are tasked with proving this statement. The energy, E, of a particle must be greater than the minimum value of the potential, V of x, for normalizable solutions to the Schrödinger equation. To build our intuition, let's first consider its classical counterpart. Imagine a generic potential energy function, V of x, as shown in this diagram. The horizontal line represents the particle's total energy, E. With this setup, we can analyze the particle's behavior. In classical mechanics, the particle's kinetic energy is given by the formula K equals E minus Vx. Since kinetic energy cannot be negative, the particle is restricted to regions where E is greater than Vx. These are called the classically allowed regions. The areas where E is less than Vx are the classically forbidden regions, where the particle cannot exist. Within the classically allowed regions, the particle's speed varies. It moves faster where V of x is smaller, since the kinetic energy K is larger, and slower where V of x is higher. So what happens at the boundaries between these regions? These are called the classical turning points. At these points, the kinetic energy K is 0, and the particle momentarily comes to rest before reversing direction. This classical perspective helps us understand why E must be greater than the minimum value of V of x. In quantum mechanics, we'll see that this restriction is just as fundamental, but it comes with a fascinating twist. Let's dive deeper into the quantum solution next. In our previous recap, we showed how the time-independent Schrödinger equation can be written as follows. Let's solve this equation for the second derivative of psi. First, notice something interesting. There are no imaginary terms, or i's, in this equation. This means we can always find solutions that are purely real. So, for simplicity, I'll assume psi is real for the rest of this explanation. Now, let's focus on the term v of x minus e in the equation. This term is key because its sign, whether positive or negative, determines how the wave function psi behaves in different regions. In the classically allowed regions, e is greater than v of x, so the term is positive. In the classically forbidden regions, e is less than v of x, so the term is negative. This sign change has a dramatic effect on the shape of psi. In the allowed regions, psi and its second derivative have opposite signs. This means the wave function curves toward the x-axis, creating oscillations. In the forbidden regions, psi and its second derivative have the same sign. This causes the wave function to curve away from the x-axis, leading to exponential decay or growth. Here's where it gets interesting. In the forbidden regions, if psi curves away from the x-axis and grows exponentially, it becomes non-normalizable. This is because a normalizable wave function must remain finite and square integrable over all space. When psi grows exponentially, the integral of psi squared, which represents the area under the curve, diverges, meaning it doesn't approach a finite value. Since the total probability of finding the particle must be 1, the wave function must be normalizable, which is not possible if the integral diverges. This shows why the energy must exceed the minimum value of the potential for every normalizable solution to the time-independent Schrödinger equation. Let's now switch to problem 2.3. In this problem, we're asked to show that there is no acceptable solution to the time-independent Schrödinger equation for the infinite square well when the energy is equal to 0, or when the energy is less than 0. This is actually a specific case of the general theorem discussed in problem 2.2, but here we're going to solve the Schrödinger equation explicitly and show that for these energy values, we cannot satisfy the boundary conditions. Let's start by recalling the time-independent Schrödinger equation for a particle inside a one-dimensional infinite square well. Inside the well, the potential is 0, so we can simplify the equation, where k squared is defined as 2 times the mass times the energy, all divided by h bar squared. For the region outside the well, where the potential goes to infinity, the wave function must be 0. This is because the particle cannot exist in regions where the potential is infinite. Let's first consider the case when the energy is 0. If the energy is 0, then k squared becomes 0. This is a simple differential equation, and the general solution is a straight line. Now, we apply the boundary conditions. For the infinite square well, the wave function must vanish at the walls of the well. First, at x equals 0, we substitute x equals 0 into our solution. Since the wave function must be 0 at x equals 0, we conclude that c equals 0. Now at x equals a, we substitute x equals a into the general solution. Since we already know that c equals 0, for the wave function to vanish at x equals a, we must have d times a equals 0. Since a is not 0, we conclude that d equals 0. Therefore, psi of x equals 0 for all positions x, which is the trivial solution. Next, let's consider the case when the energy is less than 0. If the energy is negative, we need to take a closer look at how this affects the equation. If the energy is negative, then k squared becomes positive. We define k as the square root of the negative of 2 times the mass times the energy, divided by h bar squared. The general solution can be written in terms of hyperbolic cosine and hyperbolic sine. Now, we need to apply the boundary conditions to this solution. We know that the wave function must vanish at both ends of the well, at x equals 0 and x equals a. First, at x equals 0, we substitute x equals 0 into the general solution. Since the hyperbolic cosine of 0 is 1 and the hyperbolic sine of 0 is 0, for the wave function to vanish at x equals 0, we must have c equals 0. Next, at x equals a, we substitute x equals a into the simplified solution. Now, the hyperbolic sine function is never 0 for any non-zero argument. The only way this equation can hold true is if d equals 0. Thus, we've found that c equals 0 and d equals 0. Therefore, the only solution to the Schrödinger equation is the trivial solution. So, in both cases, when the energy is 0 or less than 0, the only solution to the Schrödinger equation is the trivial solution, psi of x equals 0. This means that there is no physically acceptable wave function for these energy values. This result tells us that the energy cannot be 0 or negative for the infinite square well. The wave function must be non-zero for the particle to exist inside the well, so these energy values are not allowed. Let's analyze problem 2.4 from Griffiths quantum mechanics. This problem asks us to calculate the expectation values of various observables for the nth stationary state of the infinite square well. In an infinite square well, the wave functions for the nth stationary state are written as follows, where a is the width of the well and n is a positive integer. For the time-dependent Schrödinger equation, we attach the time-dependent phase factor, where E sub n, the energy of the nth state, is written as follows. Note that this solution applies only to the region inside the well, as the potential energy is infinite outside the well. This means the particle cannot exist outside. To calculate the expectation value of x, we revisit the general formula, where psi star is the complex conjugate of the wave function. This formula is standard in quantum mechanics and allows us to calculate the expected value of x in a given quantum state. Now, let's substitute the wave function into this formula. The complex conjugate of this wave function does not affect the real part, which is the square root of 2 over a multiplied by the sine term. However, it does act on the exponential factor. Specifically, it changes the sign of the imaginary unit I in the exponential part. When psi star is multiplied by psi, the exponential factors cancel out, leaving only 1. As a result, the time-dependent part of the wave function has no effect on this calculation. To simplify further, we use the trigonometric identity. Substituting this into the integral, we get two separate terms. Now, let's evaluate each term separately. The first term is straightforward. The integral from 0 to a of x dx equals a squared over 2. For the second term, we need to evaluate the integral involving x multiplied by a cosine function. To handle this, we perform a substitution where we define a new variable u as 2n pi x over a. After careful evaluation, the second term simplifies to 0. Thus, we are left with 1 over a times a squared over 2, which simplifies to a over 2. This result tells us that the expectation value of x is always a over 2, the midpoint of the well, regardless of the quantum state n. This makes sense intuitively because the probability density is symmetric about the center of the well. From quantum mechanics, we know that the expectation value of an operator a in the state psi is defined as the integral over all space, the complex conjugate of psi, multiplied by the operator a acting on the wave function psi. We previously used this definition to calculate the expectation value of x, which is the expectation value of position. Now, we want to use the same approach to calculate the expectation value of x squared, which is the expectation value of the square of the position operator. In the infinite square well, the stationary wave function for the nth state is given by the following equation, where E sub n is the energy of the nth state. Substituting this into the formula for the expectation value of x squared, we obtain the following integral to solve. When calculating expectation values for operators like position or momentum, the time-dependent phase factors from the wave function psi and its complex conjugate psi star cancel out during integration. This leaves the integral dependent only on the time-independent spatial wave function psi of x. To simplify further, we use the trigonometric identity for sine squared, which splits the integral into two terms. Let's evaluate these two terms step by step. The first integral is straightforward and contributes directly to the result. We solve the second integral using integration by parts twice. Here, we choose u to be x squared and dv to be cosine of 2n pi x over ax. Next, we apply the integration by parts formula. The first term is the boundary term. At x equals 0, this term vanishes because x squared equals 0. At x equals a, the sine term equals 0, so this term also vanishes. Thus, the boundary term contributes 0. We're left with the second term. Once again, we apply integration by parts, this time letting u equal x and dv equal sine of 2n pi x over a dx. Next, we apply the formula. The remaining integral is the integral of cosine. Combining the results, the boundary term contributes negative a squared over 2n pi, and the remaining integral contributes 0. Therefore, the final result of the integral is as follows. Substituting this result into the first integral, we find that the expectation value of x for the infinite square well is as follows. The standard deviation of x, often denoted as sigma sub x, measures the spread or uncertainty of the position x in a quantum system. It is the square root of the expectation value of x squared minus the square of the expectation value of x, providing a quantitative measure of how much the position varies around the average position. Having calculated the expectation value of x in the previous section, and with the result for the expectation value of x squared from our current calculations, we can now substitute these values to determine the standard deviation of x. In quantum mechanics, the momentum operator is defined as negative I times h bar times the partial derivative with respect to x. The expectation value of momentum in a given quantum state is calculated using the following integral. Here, psi star is the complex conjugate of the wave function. As we saw earlier, the expectation value of momentum does not depend on the time-dependent phase factors in psi. Therefore, we simplify the integral by considering only the time-independent spatial wave function, psi of x. Substituting psi of x into the formula for the expectation value of momentum, we obtain the following integral to solve. Since the wave function psi of x for the infinite square well is real, its complex conjugate is equal to itself. Applying the derivative operator to the wave function is straightforward. Taking the derivative of the sine function simply results in the cosine function, scaled by the factor from the chain rule. Simplifying further, the remaining part of the integral involves the product of sine and cosine functions. Next, we utilize a trigonometric identity to simplify the integral. This transforms it into a sine function that can be directly evaluated at the boundaries. Since the integral evaluates to 0, the expectation value of momentum for the nth stationary state of the infinite square well is 0. This result aligns with our physical intuition because the probability distribution for stationary states in the infinite square well is symmetric about the center of the well, resulting in 0 net momentum. Let's now calculate the expectation value of the square of the momentum for the infinite square well. We begin by substituting the momentum operator, p squared, into the formula for the expectation value. This gives us the following integral to solve. Again, since the psi of x is real, we can drop the complex conjugate, as we've already discussed. Next, we apply the second derivative of the wave function, which is a simple step in the calculation. Now, by factoring out all the constants from the integral, we are left with the following integral to solve. Once again, we simplify the integral of sine squared by applying a trigonometric identity. Now, we evaluate the integral. The result of the integral is simply a. Finally, substituting this value into our expression, we obtain the expectation value of the square of the momentum. Now that we have both the expectation value of the momentum and the square of the momentum, we can easily calculate the standard deviation in momentum. In summary, we've calculated the expectation values for position and its square, as well as for momentum and its square. Using these results, we've also determined the standard deviations for both position and momentum. It's important to note that all these expectation values are time-independent, which is why we refer to such states as stationary states. Now, let's consider the product of the standard deviations of position and momentum. This result is consistent with the Heisenberg uncertainty principle, which states that the product of the standard deviations of position and momentum must be greater than or equal to half of the reduced Planck's constant. So let's check this for the ground state, where n equals 1. The ground state comes closest to the uncertainty limit, with its product of standard deviations approaching the minimum value required by the Heisenberg uncertainty principle. That's it for today's video. We've covered the first 4 problems from Chapter 2 of Griffiths Introduction to Quantum Mechanics. I hope you found the step-by-step solutions helpful and that you're feeling more confident with the material. But we're not done yet. In the next videos, I'll be continuing with more problems from the book, breaking down each one to make the concepts even clearer. If you enjoyed this video and found it useful, don't forget to like, comment, and subscribe. Your feedback means a lot, and I'd love to hear your thoughts or questions about the problems we covered. Thanks for watching, and I'll see you in the next one.